So it's like whole note, half notes, and then quarter notes. And, yeah, it's like if I was doing it right, it should all be just a one. So it's like quarter, 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 and then it's starting at an eighth. And then it takes, but yeah. All right, anyway, now that we sort of understand what's going on here, let's see what now that we've got some idea here. In this case, he says what? You're fine. I got it. It's really fine, I got it. Don't worry about it. All right, so as he says example, all right. He claims that for this one, right, the integral of Fn is 1 over 2 to the k minus 1. Does that make sense? For 2 to the k minus 1 less than or equal to n less than 2 to the k. Which is to say, like, so the integral is, it's 1 when, like the first case, right? This is, my picture's not to scale, right? Like, this should be as tall, this should be 1 over and 1 up, you know? Fine. I think he's guilty of the same in his book. You know, his vertical and his horizontal scale for these graphs is not the same, and more power to him for the sake of typesetting. But this is area 1. This is area half. Area half. Area quarter, 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 quarter. Right? And then once you're past that case, eighth, 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 and past that, 16th. So for appropriate n, the area is just 1 over 2 to the power k minus 1. So then what does that tell us? So he says the integral of the absolute value of Fn is equal to the integral of Fn, right? Because positive, and that's equal to 1 over 2 to the k minus 1, right? And that goes to 0 as n goes to infinity, right?
But you still have to keep making higher k's.
Right, he's smarter than me. He doesn't even write this equality here. He just says goes to 0 as n goes to infinity and leaves the rest to the imagination of the reader, you know? But I do think that's not like a crazy claim or anything. So what does that mean? That means that this sequence converges to 0 in norm. Fn goes to 0 in norm. However, right? However, for every x in 0 to 1, Fn of x is equal to 0 for infinitely many n in n, and Fn of x is equal to 1 for infinitely many n in n. So the point of this is that, you know, Fn does not converge to 0 almost everywhere.
Oh, because you can't find the rules that works. Sorry, not rules that.
Oof. See, Fn of x is equal to 0. Oh, okay. Right.
X outside the group.
If you so to put this differently, if you fix any x, right? If you fix any x here between 0 and 1, there is always more points in Fn if n, there's always another point in Fn of x, which is, you know, 0 or 1. Like it just keeps oscillating between 0 and 1 as n goes on at each x, because we keep having this, you know, ever decreasing note size, which means that if you go far enough out, eventually you're going to hit 1 again. It might be 0 for a long, long time, but it's going to get back to 1. Right? Even when we get down to the, you know, like 1 over 2 to the 100th size notes, still, if you go far enough back out, you can't assuredly know that it's 0 from all on out. It's not 0 from all on out. Eventually it goes back to 1 again once you get past the, you know, 2 to the 100th. You get to the 2 to the 101, and that cycles back and makes that x that you were hoping would stay 0 back to 1 again. So you can't keep it 0, you can't keep it 1. It's oscillating at each x forever and ever. But in a kind of complicated way, right? Like the oscillation is less and less frequent as n goes on. You know? Like if I look at, you know, 0, for instance, it's 1, then it's 0, then it's 1, then it's 0, 0, 0, 0, 1. You know, if I look at like f of 0, fn of 0, fn of 0, well, f1 of 0 is 1, f2 of 0 is 1, f3 of 0 is 0, f4 of 0 is 1, f5 of 0 is 0, f6 of 0 is 0, f7 of 0 is 0, and then I think f8 of 0 is 1. And then you have to all the way to f16 of 0 to get to 1 again. And then it's f32 of 0 that gets to 1 again. And then 64, and then 128, and then 256, then a 512, then 1024, then 2048, then 4096, and things I shouldn't really remember. But anyway, you get the idea. So these two examples serve to show us that convergence in norm and convergence almost everywhere are wholly separate concepts, right? I think I've now spent entirely too much time on this, so my apologies. Are you good, Audric?
Yeah, I'm trying to put together what you're saying with the because like when you hit 32 it's like a 0.
Yeah, I'm just focusing here, Audric. Like this picture, like to see what happens at 0. I'm just looking here. This is f1 of 0.
Oh, so it evaluates to 1?
f2 of 0.
Oh, okay.
Here is f3 of 0. And so I was just noticing the pattern is once you get back to the next step size, which would be like down here, see that would be f8 of 0 is 1 again. And so like it just, as you guys figured out the way the x domain parses for different n, I mean, anyway, that's a very, very interesting example. Okay, so let us move along here. let me state the next theorem. Ay, 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 ay. If I haven't skipped over something here. Oh, he says more. He says example 2.78, which I just erased, can be used to show that in general, even uniform convergence does not imply convergence in norm. He says, however, if we assume that F1, that F and F1 and F2 and so forth are integrable functions that vanish outside a bounded interval, and the sequence Fn converges uniformly, then Fn converges to F in norm. And here's he says in this case, you're fine, I got it, it's really okay.
Sorry.
There's no need to be sorry. In this case, we have the integral of the absolute value of Fn minus F is less than or equal to b minus a times the supremum of a to b of the absolute value of Fn of x minus f of x goes to 0. And in this case, I said it in words, let me say it again. He says if f and f1, f2, are integrable functions that vanish outside a bounded interval a to b, and the sequence Fn converges to F uniformly, then Fn converges to F in norm. And so, in particular, he says we have this estimate, right? The integral of the difference of these is less than b minus a times the supremum of this. I mean, that makes sense. So you're saying that these integrals are the functions are vanishing outside the integral a to b, right? So the biggest the integral can be is the maximum, essentially, of the difference of these functions taken over that interval times the length of the interval. So I mean, it's intuitively clear what's going on here. This integral is bounded by that value. This value exists because we're assuming that Fn uniformly converges to F. Fn uniformly converging to F allows us to, make that bounded. I mean, I think that's essentially the assumption of uniform convergence, right? Like, yeah. Okay, so theorem is let F1, F2, be Lebesgue integrable, and suppose the integral of the absolute value of F1 plus the integral of the absolute value of F2 plus ... is less than infinity, all right? Then F1 plus F2 plus ... converges almost everywhere. So this is theorem 2.7.10, which I will attempt to prove over here. Oh, goodness. Such an interesting example. See here. So he says by corollary 2.54 there exists a function f which is Lebesgue integrable such that f is represented by f1 plus f2 ... By corollary 2.5.4 there exists f which is itself Lebesgue integrable, and f is represented by f1 plus f2 plus ... Now, what was corollary What was corollary 2.5.4? You guys are probably looking. Let me look. 2.5.4. Let me look back at that right quick. Page 52. All right, let me look.
Yeah, it just states exactly what you just said.
Corollary 2.54.
Yeah, it's page 52.
Oh, I'm sorry. I was on page 54. I'm an idiot.
That's what you just said. It just states there's existing.
Oh, okay. There's, great. Oh, yeah, that one I understood when I did it last time. I've already forgotten. Okay, my bad. Anyway, moving on here. Where was I? Yes. So he says, since, let's say, as f of x equals the sum n equals 1 to infinity of fn of x, for all x in R such that what? That the sum of the absolute values of the fn, the integrals of the fn, right? Oh no, just the absolute value, my bad. Such that this is less than infinity, right? It says it suffices to show that the set of all points in X for which the series is not absolutely convergent is a null set.
Oh, okay. Because it's representation on that.
Yeah. So I'll write it down here. It suffices to show the set of all x in R for which the sum n equals 1 to infinity of the absolute value of n of x not convergent is a null set. Okay, great. So he gives the name of this set, all right? Let's call that set A. He doesn't call it A, I'm saying call it A. All right? And he says let G be the characteristic function of that set. All right, fine. So then G is represented by F1 minus F1 plus F2 minus F2 plus ... I need to step away from this for a second and look at what I have to work with. So I'm assuming F1 and so forth are Lebesgue integral. I'm assuming that the integral of the absolute values is less than infinity. All right. And yeah. So I've got since these are Lebesgue integrable, there exists a limit function to which they form a representation. That's corollary 2.54. Great. And then for that function, there is a set of points the domain of that function essentially is all x for which that series converges. And the claim is that the set of points on which it does not converge has to be a null set. And supposedly we should be able to see that from this data here, right? This data here has to somehow be used. Now, if you look at so it makes sense that G would be identically 0, right? Except what? And I almost see it. I'm missing some stupid obvious thing here. Sorry, guys. Well, the next thing he does is he integrates this G here, right? And the integral of the absolute value of G is the integral of G, which is equal to the integral of F1 minus the integral of F1 plus the integral of F2 minus the integral of F2 plus dot 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 dot, which he says is equal to 0. I think what he's claiming is that this G is a null function for which that is the null. Like, remember how we define null function and null set? Like, I have to go back.
He's showing G is a null set, but how did he
I think what he's saying is that this G is the null function which defines A to be the null set.
Oh.
If I remember right, which is debatable. Let me go back here for a second. It's a null set or a set of measure 0 if its characteristic function is a null function. So
You're saying G is the characteristic function?
I think G is the characteristic. I think.
Yeah, so let's see the characteristic.
Well.
I'm sorry, I'm lost. How's he getting that representation for G?
I think he's constructing G. I think basically the argument here is let G be this. Oh, let G be the characteristic function of that set. It's not. I left out the word absolutely there. It is converged. Absolutely convergent is a null set. See, this right here, circled in blue over here, this means that this is absolute convergence of this series of integrals of absolute values of the f's, right? That means that that implies that you can rearrange the integrals of the f's. That implies you can rearrange the integrals of the f and not change the outcome of the series, right? That's absolute convergence. So the fact that we have this means that we can rearrange the integrals of the f's and not change the convergence, but that's tantamount to the fact that this is the 0 series. And then that I think then means that G is a null function, and I'm just missing some thing here. I don't know what. I'm sorry, guys. Let us go on, because I don't think this is interesting. So let's see here. The next corollary is that if you have f is represented by f1 plus f2 da 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 da, then f is equal to f1 plus f2 almost everywhere. So, I mean, you know, if you just look at the theorem, what it says, it's very nice, right? If you have f1, f2 da da Lebesgue integrable, then you can add and you know that they're integrals. The absolute value of the integrals is less than infinity if you add them all up. Then it follows that the series that you build with them converges almost everywhere, which is very nice. And the corollary to that is that if you have f is represented by f1 plus f2 plus dot 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 dot, then f is equal to f1 plus f2 plus dot 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 almost everywhere. So aha! This is what I've been wanting for a while, is that this represented is actually just a prototype for the almost everywhere convergence of series. Like I said, that's what we're going to leave this course with, I think, is this understanding that if we have a series of functions that represent this f in terms of the Lebesgue integral, in terms of everything we've built up, then that is equivalent, right? Well, not equivalent, but that implies rather that the corresponding series of functions is equal to the function being represented almost everywhere. So this really is, when I say represented, I could say f is equal to f1 plus f2 almost everywhere. Every time I said represented, we could have just as well been saying the series is almost everywhere equal to its limit. So there, by the way, is the downside of you guys being the guinea pigs for me teaching this, is because if I was teaching this for the third or fourth time and regularly, then I would have been telling you that from the start. You know, I've taught this material vaguely like once before, and I never quite had a course in it either. So, well, I might have had a course in it, but I forgot. Where was I? So then there's one more theorem in this section, which is that, okay, so this theorem. Can I erase Audric?
Yeah, you're good.
Okay. And I really think the thing we're missing from what I'm erasing right now, it's nothing big. Like, it's just a matter of getting past the word salad of like, it's not in that set kind of thing. And like, my brain is not processing not in something at the moment. So that's my fault, but truth in advertising. So here we go. Theorem 2.7.12. Here we go. Let f1, f2 da 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 be Lebesgue integrable, and suppose they're nice in the sense that the integrals of their absolute values sum up to something less than infinity, then f1 plus f is equal to f1 plus f2 plus dot 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 almost everywhere, if and only if f is equal to f1 plus f2 plus dot 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 in norm. Okay, so we finally find some common ground to convergence almost everywhere and convergence in norm at the level of series of Lebesgue integrable functions subject to this condition. So if we have a bunch of functions that are Lebesgue integral such that the series formed by the integrals of their absolute values is less than infinity, then the sum of the functions, the series built from these functions, converges almost everywhere to the same function that they converge in norm to. So here we have an agreement between the almost everywhere concept and the in norm concept. The proof doesn't look too bad. Okay, so he's like, by corollary, 2.54 again, you have G, which is represented by F1 plus F2, right? And then by theorem 2.66, you get G is equal to F1 plus F2 plus dot 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 in norm. How is that? Do I have theorem 2.66 on the board? Or is that from that's from last time, isn't it? What was theorem 2.66? So that one, that one just says that if you have F represented by F1 plus F2 plus dot 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 dot, then the sum of F1 and F2 converges to F in norm. So it's just, that's immediate. So that's an immediate consequence of corollary 2.54 applied to the function G, which is built from adding together the Lebesgue integral functions. All right, and then what? So then by corollary 2.711, which I think I just wrote down here, maybe. Yeah, this is 2.711. So by that corollary, we have that, since it's that corollary says that this implies that G is equal to F1 plus F2, right? Almost everywhere, right? This is corollary 2.7.11 because we have G is represented by F1 plus F2, which means G is equal to F1 plus F2 almost everywhere.